Now, last time we were doing free radical substitution of different molecules, ठीक है, and we had talked about uh, termination, initiation, and propagation steps. ठीक है, just quickly going through that. Okay, you had free radicals, chlorine and bromine would go and react with alkanes. Chlorine, because of UV light, would uh, homolytically break. It would be homolytic fission. Let me add those words as well. So over here, there would be, okay, just adding homolytic fission over here. So there's going to be homolytic fission, and they would homolytically break, producing free radicals. And then those free radicals would start attacking the alkane, the hydrogens from the alkane. They would start stealing them, and Cl would bond with the H, and the C would be left with incomplete bonds. And it's going to become a methyl radical. And the methyl radical would then steal one of the chlorines from the chlorine molecule, which is already undergoing homolytic fission. So it would pull its electrons and bond with it, and one of the Cl would get substituted, and the reaction would keep on repeating. Every time a Cl radical is produced, it's going to take away one of the hydrogens, and the whole process would repeat again. And every time another Cl would get substituted, and then you had a termination step in which what would happen was that any of the two free radicals, this was the termination step at the end. Any two free radicals that are getting formed, they would combine to form a molecule. Now, a few things to remember about this is one of them is hydrogen gas is never formed. ठीक है, so small points. Hydrogen gas is never formed since there is as no H radical is formed. So in any of the steps, there is no hydrogen radical ever being produced. If an H radical had been produced, then in the termination step, two H radicals might have gotten together to form an H2 gas molecule. Since there is no evidence of H2 gas being produced, which means that there is no H radical. Okay, so remember that. And another thing about this is that tetramethyl lead 4, so tetramethyl lead 4 is used as a catalyst. And why is it used as a catalyst? As it is a source of methyl radicals. So it's a source of methyl radicals. What that basically means is that why is the reaction happening? The reaction happened because there were free radicals, and those free radicals, they started attacking the hydrogen atoms of the alkane. So if you have more free radicals, then obviously the reaction is going to be faster. Tetramethyl lead is it's going to be Pb CH3 and bracket 4. So that is what tetramethyl lead is. Okay, just remember these two small points so we can move on. Now we're done with alkanes, and sorry, one more important point was, which should be added over here, is that free radical substitution is not just limited to alkanes. It could happen to any carbon chain. It can happen to any carbon chain if UV light is present. So it's not just purely alkanes. It could happen to anything. For example, if you have a carboxylic acid, a propanoic acid molecule, and you react it with Cl2 under UV light, what's going to happen is that, and since it's a random reaction, any of the hydrogens in propanoic acid could be substituted by Cl, and HCl would be produced. Sorry, HCl would be produced as a byproduct. So remember, it could happen to any carbon chain which has carbon and hydrogen atoms, and you react it with Cl2 under UV light, and you're going to get this reaction. So is this clear? Abba, Rida, is this clear? Minahil, clear? Bazga?
Yes.
Yes, sir.
I said now, the next thing that we're going to discuss, it's cracking of alkanes. Or the better term would be cracking of long chain hydrocarbons. So cracking of long chain hydrocarbons, what happens in that cracking? As a first thing, what's wrong with long chain hydrocarbons? Any idea? Minahil, any idea?
Can you repeat the question?
What's wrong with long chain hydrocarbons? They're not very useful. Okay? So why are they not very useful? You've done this in O levels. The reason they're not very useful is because if it's a long chain hydrocarbon, it's going to have more van der Waals forces. It's a bigger molecule. So if it has more van der Waals forces, if it has more attractive forces, because it's a long chain molecule, it's a big molecule, so it's going to have high melting and boiling points, and it's going to be very viscous. Okay, the bigger the molecule, the more viscous it's going to be. Okay, it's going to be thick. It would be hard to move. It would be more wax-like, and it would be less flammable as well because it's not going to mix with oxygen. The bigger the chain, the more van der Waals forces, temporary dipole induced dipoles there would be. So the chain, like if you have very big molecules, then the chains would be attracting each other, and oxygen would not be able to mix with them. Okay, so they wouldn't because all the chains are very strongly attracted to each other. So like waxes and other polymers like plastics, long chain hydrocarbons are very viscous, less flammable, and they have high melting and boiling points. Is that clear? Baza clear? Abba, is this clear?
Yes.
Yes, sir.
So long chain hydrocarbons are not very useful and they're broken down into smaller, more useful chains. So they would have low melting and boiling points, like they're going to be gases or volatile liquids which flow very easily. So they're less viscous as well, and they would be more flammable as well. So they're going to be more flammable as well. How do you break them? The conditions for this reaction are that you use high temperatures, which are usually greater than 450 degrees centigrade, and you use a catalyst. And the catalyst is Al2O3 and SiO2. It could be any one of them, or it could be both. Usually, where do you get Al2O3 and SiO2? You get it from rocks, which are called zeolites, minerals that are called zeolites, and there's another one which is called pumice. So that's these are the conditions for cracking of long chain hydrocarbons. Okay, just remember that. Uh, Most of it is O levels. And one thing that you should remember about cracking is what happens in the cracking reaction. Okay, let's say you have a big molecule, 50 carbon atoms, and H is what is 2n plus 2? That's 102. And you crack it. One thing that has to be remembered about this is that it's going to break up into smaller alkanes and alkenes, and it's going to be a completely random process and hydrogen gas. So it's either going to be one of these three or all three or just two of them. It depends. But whatever happens, remember this that the number of carbon atom and the number of hydrogen atoms must add up to 50 carbons and 102 hydrogens. So, for example, there's an alkane with 20 carbon atoms and H is 42. So, when you're making an equation, remember the general formula of an alkane, which is CnH2n plus 2, which I've already told you earlier as well that it's not necessarily this one, it could be different as well. And alkenes, it's CnH2n. So I can break this molecule into an alkene as well. Now, whatever happens, um, the total number of atoms should remain exactly the same. So you can count, you can add up the hydrogens and you can add up the carbons, and you're going to get the same thing. But it has to be a mixture of alkanes, alkenes, and hydrogen gas. We can do another reaction. Let's say I get two alkenes. So I get C10H20, and I get another one which is, let's say, C40 and H80. Now, as you can see, if you total them, you would be short of two hydrogens. So there would be, whenever you're short of two hydrogen, that means hydrogen gas would also be produced in the reaction. So this is what's going to happen. Alkanes, alkenes, and hydrogen gas are going to be produced when you crack molecules. Okay, is this clear? Hiba, is this clear? Ibrar, is this clear? Minahil, clear है?
जी
Yes, sir. सर एक क्वेश्चन है कि पहले वाले क्वेश्चन में what you're doing is कि if alkanes or alkenes दोनों produce हो रहे then hydrogen won't be produced. लेकिन if both of them are alkenes then hydrogen will be produced.
But even that is not necessarily true. What you just check is if you add them up. I mean, because a molecule could break into a number of small pieces. Okay, it could be C5H10, then there could be C8, 816. Ibrar, are you getting my point? Okay, so I've broken it up into two very large chunks, right?
Mm-hmm.
What you just have to check is, okay, add them up. If you're still short of hydrogens, then add hydrogen gas. Is that clear?
Oh, अच्छा yeah, exactly. सही.
So just remember that. So it could be, I mean, there could be another version. So even with alkanes, you might get hydrogen gas. Okay, it depends. And remember, the products are completely random. So the only thing is they should add up to this molecule over here. So we're pretty much done with alkanes. And let me, I think I had a syllabus somewhere. हाँ ठीक है. अच्छा, just let me just this is the 2021, the latest syllabus. Remember, the dark ones are the ones that are in A2. So we did isomers, sigma and pi bonds. We did so alkanes is um, cracking. We're done. Uh, Crude oil, the fractional distillation of crude oil, we can do that later. That's O levels. But do you know what aliphatic and aromatic is? Any idea? Anyone? Bhaskar, any idea what aliphatic is? And what is aromatic?
No, sir, never heard of the words.
So I'll just, I mean, it's just one line. Whatever you are studying is aliphatic, right? Aliphatic is anything. It's how would I state aliphatic? Aliphatic is hydrocarbons. Well, I'll just simply explain all the molecules that you're studying. TK, that you are right now studying. Aromatic is. Did we do the structure of benzene earlier? I think when we did sp3 sp2 hybridization, did we? Just one second, let me quickly see. Achha, we actually didn't do benzene. Achha, we're not supposed to do benzene. We just need to know the structure of benzene because that's an A2. Okay, so we did not do benzene. Let me quickly draw benzene. Now, anything with benzene is aromatic. Benzene is referred to as an aromatic molecule. So any molecule that has benzene in it, and aromatic is from aroma, that they have a certain smell. And so all compounds having benzene are going to smell a lot. It could be a good smell, it could be a bad smell, but they would have a certain smell. So they're referred to as aromatic. Now, what is benzene? Because the structure of benzene is in your course, otherwise, it's not really in your course. Benzene is this thing. So I'm going to quickly draw the structure of benzene. So it's 6 carbon atoms in a cyclic arrangement, and they are alternating double bonds. Now you can see that each carbon atom is identical. Now this structure over here, you can remember the structure is in your course. Now this structure over here is known as the Kikula structure. And this is not the CIE representation of benzene. The reason I've drawn this structure is because it's easier to actually understand this structure. Now I'm going to move towards the CIE representation of this structure. Whenever you're confused with benzene, think of benzene like this. And then you'd be able to figure out how many bonds is each carbon atom making. So it's like carbon making 4 bonds. Each carbon is making 4 bonds. Each carbon is identical. It's making a double bond with another carbon atom, and it's bonded to hydrogen. Same with this carbon atom. Same with this carbon atom. So they're all exactly identical. मुझे बताओ कि what happens when carbon is making a double bond? Is it sp3 hybridized or sp2 hybridized? Anyone?
sp2.
Okay, so this is
sp2.
okay. This is sp2 hybridized. All of them are sp2 because it's only bonded to 3 atoms. So now I'm going to draw the structure that CIE wants. So you have carbons, and each carbon is sp2 hybridized, which means that it's bonded to 3 atoms, right? So that's carbon and carbon and okay, so there's 6 carbons in a ring shape, and each one has a hydrogen coming bonded. So each one is fan shaped. Okay, my mic is on. So each one of them is fan shaped. Okay, remember carbon has 4 electrons. Now, when you have sp2 hybridization, carbon, 3 of the electrons of carbon, they bond with other carbon atoms, and the 4th electron is not doing anything. So there's a 4th electron, which is apparently not doing anything initially. So same over here, there's a 4th electron, a p orbital, not doing anything. There's another 4th electron, not doing anything. So each one has this spare electron. And when you have p orbitals that are in parallel to each other, they start forming double bonds, right? They would start forming sigma pi bonds. They would start to overlap above and below the sigma bond that's already there. These two would start overlapping, with each other. And same is true for these two. They would start overlapping, right? Is this clear? So you're getting three double bonds. Ibra, is this clear? Rida, Hiba, Minahil, is this clear?
Yes, sir.
Now,
Yes.
now the issue is that when you have 6p orbitals, focus on this carbon atom over here and this p orbital over here. If it's capable of overlapping with the carbon atom on the right and forming a pi bond on the right, it could also do exactly the same thing with the one on the left, right? So what actually happens is that when you have 6 orbitals, the double bonds, they kind of mix up. They all kind of, this is called resonance. Uh, the double bonds, I mean, why is this p orbital bonding with this one? It could also bond with this one. So what ends up, what you get at the end is that they all start overlapping with each other. And at the end of the day, all 6p orbitals, they get delocalized. So there's a pi electron cloud on top and below the structure of benzene. Do you get this? Is this clear? Abba, is this clear? Rida? Ibra, is this clear?
Can you explain this again?
नहीं वो था ना कि each carbon atom was making a double bond, right? Pi electron cloud.
जी, exactly.
मतलब each one had a p orbital, right?
Mm-hmm.
So in this structure, they're showing a double bond over here, which means that these two are overlapping and these two are also overlapping, right? Ibra?
Overlap. Yeah. जी.
But when you have 6p orbitals that are in parallel to each other, because each carbon atom is identical, it has this spare orbital, right? Which
Mm-hmm.
is not bonded to any. I mean, there is no fourth atom, right? So
जी.
when you have 6p orbitals, they all eventually end up start overlapping with each other.
All right.
So whenever you have alternating double bonds, what eventually happens is that the double bonds, they mix up, and the structure of benzene, the CIE structure of benzene, is actually it actually looks like this. That it's going to have so the CIE structure of benzene is going to be something.
Oh. अच्छा.
It's going to be like this. You must have seen this in a lot of places. This is the skeletal formula. These are the carbon atoms, and each carbon atom would be uh, bonded to one hydrogen. So there would be one hydrogen that would be bonded to each of the carbon atoms, right? So that's so you don't actually show these double bonds. You show a ring which has delocalized electron cloud. The reason I actually like this structure better is because you're able to figure out the bonds correctly. You're able to figure out the hybridization correctly, and you're also able to figure out the bond angles correctly because in this the bond angles are going to be it's going to be fan shaped 120 degrees and trigonal planar, which is the same
Sir,
over.
but
Huh.
sir, trigonal planar में we have the angle 120, लेकिन if we recall those compounds, which is boron trifluoride,
Yeah.
so it was also trigonal planar, but the point was कि it had single bonds in all of those bonds.
Mm-hmm.
So, and this molecule over here has 3 bonds,
नहीं, हाँ,
but
ठीक
one
है,
of them is a double bond.
so basically it's not going to be exactly 120, right? That's your question, right?
Yeah.
ठीक है, लेकिन approximately it's going to be 120.
ठीक.
ठीक है, मतलब there's going to be some slight difference. अभी तो मैं बिल्कुल general बात कर रहा हूँ, ठीक है? So is the structure of benzene clear? It's going to be hexagonal and it's going to be completely planar because each atom it's like connecting fans together. So it's going to be hexagonal and planar. Is this clear? Abba, Minahil, is this clear?
Clear.
Asha, so whenever you hear the term aromatic is benzene. And we did a lot of past paper questions where we did see this structure a lot. Uh, I mean, it's a very stable arrangement. This thing is a very stable arrangement, and it exists in a number of organic molecules. Uh, so you have a lot of molecules with which have benzene, and these hydrogens they could be something else as well. Like it could be Cl, it could be OH. But anyways, that's the only thing that you need to learn about benzene. This is the only thing that you need to learn about benzene. I have not yet seen any question. It is in your syllabus, in the AS syllabus, but I have not yet seen any questions that are directly linked to benzene. And so let's have a look at the syllabus once again. If we have missed anything, we did. I said we can do combustion later. All organic compounds combust, so we can do that. We can do crude oil. It's exactly the same as the one that you did in O levels, fractional distillation of crude oil. So forget that for now. Let's start with alkenes. Now, quickly, alkenes. So alkenes are hydrocarbons, but they are unsaturated hydrocarbons. So you have a carbon and carbon, it's going to be sp2 hybridized, and there's going to be double bonds. And quickly drawing the pi electron cloud, it's carbon is bonded to 3 atoms. This carbon is also bonded to 3 atoms, and the fourth orbital is going to end up forming a it's going to form a pi electron cloud. And the pi electron cloud is the reactive part of the molecule. So that's the reactive part of the molecule. It's a high electron density pi electron cloud, or we can say it's an electron rich center. Lots of electrons over here. So all alkenes pretty much have this. About the physical properties, I'm just going to write that the physical properties are almost the same as alkanes. So whatever you studied in about alkanes, that they were non-polar and they had van der Waals forces, their melting and boiling points were low, and they were not soluble in water because they can't form hydrogen bonds. So alkenes, they have exactly the same physical properties as alkanes. Whatever we studied about alkanes. Now, focus on the double bond over here. All alkene reactions are going to be because of this double bond here. The double bond over here is electron rich. It's an electron rich center, and anything that's attracted to this electron rich center, that's called an electrophile. So electrophiles are going to be attracted to it. And all of alkenes reactions are going to be electrophilic. So we're going to talk about electrophilic reactions, and we're going to talk about the reactions that you studied in O levels first, and then we're going to move towards their mechanism. So alkenes had addition reactions, but now they would be called electrophilic addition reactions. ठीक है, is this clear? ये electrophile, Mihail, is this clear?
Yes.
So electrophilic addition reactions. ठीक है, it's the same as the addition reactions that you did in O levels. The first one, number one, was called bromination. I remember we're going to revisit this, and we're going to talk about their mechanism. नहीं, बल्कि we can talk about the mechanism right from the first. I'll talk about the mechanism right away. So the first one is bromination. bromination is a reaction with Br2. You have an alkene. Let's say there is this alkene, and it reacts with a Br2 molecule. Now, the Br2 molecule could be in aqueous state, or it could be in an inert solvent. Like CCl4. So the reaction is bromine, and the thing that would react with bromine is it's going to be an addition reaction. It's going to be these two carbon atoms, the ones that are involved in this double bond. The rest of the molecule nothing should happen to the rest of the molecule. So what would be the products? The products would be that you'll have CH3. The double bond is going to vanish. It's going to go away. And on both these carbon atoms, bromines are going to get added. And the only condition that is needed is absence of light. Because with light, you get free radical substitution. I mean, you get free radicals, bromine forms a radical, and uh, all these random hydrogens, they get substituted. So with light, free radicals are formed, which would start pulling electrons from the hydrogens or would start stealing the hydrogen atoms, right? So there should be absence of light. Bromine should be either aqueous or in an inert solvent, and you get this reaction. And remember, if aqueous conditions are used, then another thing could happen, and that is that OH could get involved. So instead of both BRs getting added, you could have an OH that might get attached to the molecule. So in aqueous conditions. So remember that about aqueous conditions, that chances are that OH might also step in and could disturb the addition reaction. Does anyone know the significance of this reaction? Where was it used and why was it used? Bromination of alkenes. Anyone from O levels? What was the main purpose of
Sir, to test these hydrocarbons.
exactly alkenes? Basically, it was a test for
Exactly.
identification of alkenes.
It would decolorize, I guess.
Yes. So this was used as a test for identification of unsaturated hydrocarbons. Not hydrocarbons, anything that is unsaturated. Any molecule that has carbon, double bond carbon. Red brown bromine or orange, also referred to as red brown bromine, is decolorized. So this was basically the reaction that you've studied. You can remember the reaction only happens with the double bond and nothing else. So if you have a large complicated molecule, so let's say this is, so remember this is not benzene, okay? Benzene has the resonance going on, multiple double bonds, three double bonds alternatingly. So you have this molecule and there's another double bond here, and there are two hydrogens with this, one hydrogen with this. There's going to be one hydrogen here, two with this, two hydrogens, and so if bromination happens to this molecule, So if bromination happens to this molecule, what's going to happen is that so on all the double bonds, bromine will get added. So there's going to be bromine added here, bromine added here. Only, and nothing happens to the rest of the molecule. The rest of the molecule remains exactly the same. So there's going to be an H here, an H here, two H's here, two H's here, one H, and this would have two H's. So it only gets attached to the double bond. Brad, is this clear?
Yes sir. Sir, if there was only one bromine molecule, तो फिर ऐसा हो सकता है कि one of the bromine atom binds to one of the double bond वाला carbon और दूसरा दूसरे के साथ, kind of that reaction.
नहीं क्या मतलब if there was only one bromine molecule?
मतलब you're adding bromine,
अच्छा
मतलब you're adding 4 bromine atoms, huh?
हाँ, so
And
there's
there
two.
is only exactly. So in case if there was one bromine
नहीं,
molecule,
that's not possible. मतलब
अच्छा ठीक.
if there was only one bromine molecule, so either it's going to bond over here or it's going to bond over here.
ठीक, that's
ठीक है, ये split नहीं होगा, ठीक है?
ठीक.
अच्छा, anyways, mechanism of the reaction. Let's talk about the mechanism. And we did one free radical substitution mechanism, so let's quickly try and do this. As I'm going to quickly explain what happens. As you have this molecule. Let's take a simple ethene molecule, which has these pi electron cloud. There's a double bond in the middle. So there's a double bond in the middle with electrons. This is the electron-rich center. If a bromine molecule comes sufficiently close to this and it collides with it, what's going to happen is, you can focus on the reaction mechanism. What's going to happen is, and this is it comes very frequently, that bromine molecule is going to get polarized. Its electrons are going to get repelled. So I'm drawing a full arrow. Why is it getting repelled? Because of the electron-rich center over here. There's a lot of negative charge here, and that negative charge is repelling the electrons over here. Is this clear? Abba, is this clear? Rida, Abba, is this clear? Minahil?
Yes.
Yes.
Achha, so because of the large number of electrons here, these electrons get repelled, and that polarizes the molecule. This bromine molecule, it becomes positively charged. This one gets a partial negative charge, and the positive bromine would then start attracting these pi electron clouds. It's going to start pulling these pi electron clouds towards itself because it's positive. And if the electrons get further attracted to it, this Br would get repelled. So at the end of the day, what happens is that the molecule breaks off. I mean, there's heterolytic fission happening, right? Why is it heterolytic? Because both electrons in the bromine bond, they actually go to one of the bromines. So there's heterolytic fission happening and the bond is breaking off. So what's the next step? The next step is that you had a pi electron cloud, and let me draw that quickly. So the next step was, here's your pi electron cloud, and here are your bromine. The bromine molecule has broken away. It has fission heterolytically, which resulted in the formation of a Br plus one and a Br minus one. Now this Br plus one is going to strongly pull these electrons, pi electron cloud, towards itself. And that is what happens. All the pi electron cloud, it gets attracted to this Br positive. So the Br positive pulls all these electrons towards itself. and your pi electron cloud, the 2 electrons in the pi electron cloud end up with this Br. Is this clear? ठीक है, is this clear to everyone? Ibrar, is this clear?
Yes, yes, sir, yes, sir.
ठीक है. Baza, is this clear? So,
Yes, sir.
अच्छा, so Br positive, वो जो pi electron cloud that was over here, that gets pulled by this Br positive, and it's no longer going to be positive because it got its electrons, right? So it's no longer positive. But this carbon atom over here would become a carbocation. This is known as a carbocation. Why? Because the double bond had its, I mean, this carbon had its electron as well, and this Br took that electron away from it. So this carbon is now electron deficient. It has a positive charge. So this is known as a carbocation intermediate.
Sir, ये positive charge क्यों है यहाँ पे?
Well, focus on this. The Br positive was taking electrons from the pi electron cloud, right?
जी.
The pi electron cloud, there was 1 electron of this carbon atom as well, right?
Mm-hmm.
So when it pulled the electrons away from the pi electron cloud, so or
अच्छा, because it pulled both of the electrons.
exactly. इसको तो कुछ नहीं हुआ ना, वो तो मतलब
जी,
ये
जी.
पहले इसके साथ bond कर रहा था, it was bonding with this carbon atom.
जी, जी, जी.
Now it's bonding with the bromine, so it didn't actually lose the electron, ठीक है? So the electron was still there. I mean, instead of the bond being made with this one, it's now making a bond with this one. इसका मसला हो गया क्योंकि when it pulled the electrons,
It lost one of its electron.
हाँ, तो one of the electron was taken away by this bromine, जिसकी वजह से it's no
जी,
longer
जी.
positive, but the other one is now
Exactly.
positive. And the next step is the Br minus one, which was initially getting repelled, is now going to come in with its 2 electrons, and it would bond with this carbocation, and that's how 2 of the bromines are going to get added up. Okay, just is this clear? Just remember, this is not the CAE mechanism that they want you to draw. When next class, I'll draw this. We'll start with this. But is the whole idea clear? Why bromination happens?
Yes, sir.
Yes, sir.
Yes.
So, Binail, is this clear? Ida, is this clear?
Yes.
So we'll continue with this. Just remember, okay, I'll draw this in the next class. Okay, what would CAE expect from you? Okay. So we'll continue with this in the next class then. Okay then.
Chalo, thank you, sir. Allah Hafiz.
Allah Hafiz.
Allah.
Allah Hafiz.